Chapter 2 is discussing the elasticity, is discussing the elastic properties of solids. We want in this chapter to study the deformation of an object, which means the change in shape or size or both, when applying external forces to the object. We will apply two external forces equal in magnitude and opposite in direction to this rod. Deformation happens to the object. However, internal forces of the object resist this deformation. So we will find that the object will try to resist this deformation, F internal and F internal. This is the internal force. But deformation happens when changing the shape or size of the object. This is the studying of elasticity of the solids. In this chapter, we want to know the deformation that happens when applying these forces, but we will study it from the point of view of stress and strain. These are two concepts that discuss the deformation that happens because of external forces. We will study three main parts: the elasticity in length, the longitudinal elasticity, the volume elasticity or bulk elasticity, shear elasticity. Let's begin with the elasticity in length or the longitudinal elasticity. Assume that we have a rod whose length is x naught initially. X naught is the initial length of the rod. We will apply force F. I'm fixing the other side of the rod. Either I apply two external forces like this, or I fix one side and apply force from the other side. So the wall effect is the other force. This is equivalent to this. These two situations are equivalent. What happens when I apply this force F? Elongation happens or change in length of the rod happens. This is the deformation that will happen to the rod. Also, the rod try to resist this deformation. So we have internal forces in the rod trying to resist this deformation. Studying these forces and deformation started by Hooke. Hooke, the scientist, Hooke discussed that this internal force is proportional to the delta x. Delta x is the elongation. When you apply force, there is increase in length called delta x. So Hooke said that this force is proportional to delta x. The internal force is proportional to delta x. It's trying to resist this change in length. So we can say that F equals constant delta x. F equal constant K delta x. This is Hooke's law. Hooke's law is saying that the internal force that we have in the rod due to applying external force F capital equals negative K delta. Negative means it's a restoring. It's trying to resist the change in delta x. I'm trying to resist this because F internal is in the opposite direction of delta x. That's why we are putting the negative sign. This was the first scientists to study the elasticity of this rod under the effect of the applied force. But scientists found that it's better to study stress instead of force. Stress is the force per unit area. We want to study the stress, not the force. And we want to study the strain, not the change delta x. The strain is the relative deformation that will happen in the rod. So instead of studying force and change in length, we will study the stress and the strain. What is the stress? The stress is the force acting per unit area. The symbol of stress is T, and it is T equals F over A, force per unit area. The unit of stress is Newton per meter square, which is the unit of force divided by the unit of area. We will study the strain. The strain symbol is epsilon. Epsilon is the symbol of strain, and its definition, it's the relative change in the dimensions of the object, which in our case, not delta x, it's delta x related to x naught. This gives clear explanation for us. So strain means the degree of deformation, and it is the relative change in the dimensions. So it's delta x over x. Because it is a relative change in dimensions, we don't have units for strain. So we want to study the elastic properties of the materials in terms of stress and strain. You will apply force on this rod. This force, you will see it as force per unit area, which is stress. The rod will be deformed. It will have change in length, delta x, and this relative change is called strain. So when you apply force, you have stress, and when you have stress on the object, deformation is delta x, which we will express it in strain delta x over x. What is the relation between stress and strain? For sure, if you increase the stress, the strain will be increased. So the relation between stress and strain is proportional to each other's. T is the stress force divided by the normal area. Strain is delta x over x naught. And the relation is proportional. They found that the strain is proportional to the stress applied. So stress proportional to strain. But take care. This is for small stresses only. For small stresses only. When I have larger stresses, the relation will differ. According to this relation, we can say that the proportionality sign could be equal and constant. The first rule we have is stress equals constant multiplied strain. This constant for longitudinal elasticity is called Young's modulus. T is the stress equals E, Young's modulus, multiplied by epsilon, which is the strain. Young's modulus unit is Newton per meter squared because the unit of stress is Newton per meter squared and the strain have no units. So the units of Young's modulus is Newton per meter squared. If I want to draw the stress with the strain, it will be a straight line, and the slope of the straight line will be Young's modulus. Young's modulus is also called longitudinal elasticity modulus because it is the modulus used when we are talking about longitudinal elasticity or elasticity on length. Also, some references use the symbol Y capital. So, Young's modulus in our course, we refer to it as E capital, and in other references, maybe you will find it Y. Take care that Young's modulus is a positive modulus, or the moduli of elasticity must have a positive value. It's never negative. Let's discuss two cases. The first case, when we have tensile force. When we are applying tensile force, the stress is tensile stress and the strain is called tensile strain. When you apply this tensile force, you are trying to increase the length. So delta x will be positive value, Delta x means the change in the length of the rod. The other example is when we apply compressive force. When we apply compressive force, the stress is called compressive stress and the strain is compressive strain. When we apply this force compressively, it's trying to decrease the length of the rod. So the change in the rod length is negative. Delta x will be negative because it is decrease in length. So you will have your compressive strain negative. If I put the compressive strain here negative, I must put the compressive stress negative in order to have Young's modulus positive. That's why in dealing with compressive force, we put the stress in negative value. So in the longitudinal elasticity, we either have increase or in length or decrease in length. Take care while dealing with compressive forces, you put the stress force over area and you put a negative sign. This will assure that the Young's modulus is a positive value. Okay, what will happen if the stresses are not small? We said that stress and strain are proportional, but let's see the stress strain curve for all values of stresses. This is the relation between the stress on the y-axis, its symbol is T and its unit is Newton per meter square, and the strain on the x-axis, its symbol is epsilon, and it doesn't have any unit because we mentioned before that the strain is a relative change in the dimensions of the rod. If you apply stress on the rod, it will make strain proportional to it till point number 1. Point number 1 is called the proportional limit. This is the last point of proportionality between stress and strain. After this, the relation will not be linear. It will be curved like this. As you apply more stress, the strain is increased, but not linear relation. So we say that point number 2 is called elastic limit point. As you apply more stress, you will find that the material has elastic region. You apply stress and the stress strain curve takes this figure. Point number 3 is called yielding point. What's the meaning of yielding point? Means that if you remove the stress, the material will not be back to the same dimensions before. Let's explain it in another way. In this region, we say the material is elastic. Elastic means if you remove the stress, the strain is gone. I apply force like this on the rod. So strain appears. Force over area means stress. Delta x over x known means strain. If you remove the force, the strain vanishes, disappears. This means elastic region. Elastic region. In any point, once you remove the stress, the strain is gone. Strain is zero. But starting this region after point 2, if you remove the stress, the strain is not removed completely. You will find the deformation is permanent. يبقى that's why in the plastic region we have permanent deformation. Permanent deformation. Although you removed the stress, but the rod didn't be back to its original length. Point 3 is called the yielding point. Point 4 is called the ultimate stress. It is the maximum stress you can achieve. Point 5 is called the breakdown or the rupture point. This is the stress strain curve. It differs from a material to another. We make experiments in the laboratory to determine the stress strain curve for every material. As I mentioned, point 1 is called the proportional limit. Point 2 is the last point of the elastic region. It's called the elastic limit. Point 3 is called the yielding point. Point 4, ultimate or maximum stress. Point 5 is the breaking or rupture stress. As an engineer designing any application, I cannot work in this region. Why? Because permanent deformation happens. So I must work in this region. And also, I can't work from 1 to 2 because now I don't know the relation between stress and strain. So as an engineer, I want to work only in this range. So I work maximum on the proportional limit because stress and strain relation is known. Also, according to codes of application, we specify safety factor. Safety factor is the proportional limit stress divided by the working stress. For an example, if I have T proportional this point, I will make working stress in a point less than the T proportional for safety. For safety, according to T proportional over safety factor. If I have safety factor of 3 and T proportional 100, so I'm working on a point 100 over 3. This stress strain curve helps me to understand the nature of every material I'm using while designing certain application. So we want to make all our working stresses in this part. And it's better to be less than the proportional limit by safety factor according to the code used in every application. Now I want to get the relation between Hooke's law or Hooke's constant and Young's modulus. As we mentioned before, stress equals Young's modulus multiplied by the strain. Remove the stress and put F over A, force per unit area. Remove the strain and put delta X over X naught, relative change in the dimensions, and Young's modulus here. So the force equal in one side, put the force equals EA over X naught delta X. From Hooke's law, Hooke's was the first one to study the elasticity, but he studied the elasticity from the force point of view. I'm comparing Hooke's law with this law. So by comparison, K equals EA over X naught. This is the relation between K, EA over X naught. This is the relation between Hooke's constant and Young's modulus. If we return back to the stress strain curve, when explaining the elastic region, we said removing the stress will remove the strain, and the material will regain its original dimensions x naught. What makes the material go back to its original size? Stored energy. So we have stored energy in the material, which returns it back to its original size while I am in the elastic region and I am in the proportional region. So we calculated the energy stored in the material, which is capable of returning the rod to its original length. The energy stored in the material energy stored in the material could be calculated as half stress value, strain value multiplied by the volume. This is the energy which is capable of returning the initial dimensions of the rod after removing the stress. This energy is calculated by the joule, but I am interested in the energy density stored. The energy density stored means energy per unit volume, so joule per meter cube. Divide the energy by the volume, so you will get rid of this term. The energy density stored is half stress multiplied by strain. If you examine this curve, this is the area under the curve because the area of the triangle is half base multiply height, so it's half stress strain. You can also use any of these forms instead. Okay, now we want to know what happens in the other side. If I have this strain, delta L increases. What happens to the diameter? So checking the diameter, if we apply force, which will increase the delta, the length of the rod by delta L, of course, the diameter will be decreased by delta D. That's why we want to understand what is transverse strain and what is Poisson's ratio. The transverse strain means the deformation that happens in the other side. We are talking about the length. What will happen to the diameter of the rod? So if we say that the longitudinal strain is delta L over L naught, we have change and deformation that happens also in the diameter. This deformation is relative to the initial diameter delta D over D naught. That's why we called it transverse strain. So examining the diameter, we have deformation. This deformation is not along the axis of the force. It's perpendicular to the axis of the force. So transverse strain is the strain or the deformation that happens in the perpendicular axis. Then we define what is called Poisson's ratio. Poisson's ratio is the ratio between the transverse strain and the longitudinal strain. But by definition, we put a negative sign in the law. Why we put negative sign in the law? Because we must have Poisson's ratio positive. Let's discuss what will happen if this force is tensile. If this force is a tensile force, it will increase the delta L. So the change in delta L will be positive and the longitudinal strain will be positive. But it will decrease the diameter. So the change in the diameter will be negative and the transverse strain is negative. So you will divide a negative over positive, which will make the Poisson's ratio negative. I don't want it to be negative. I want Poisson's ratio to be positive only. That's why in the law we put negative sign to be sure that Poisson's ratio is a positive value. There is another kind of deformation that may occur in the rod, not due to forces, due to heat. We know quite well that if a rod is subjected to change in temperature, if we increase the temperature of the rod by heating, it will increase in length due to expansion. This is thermal expansion. Okay, this is a kind of deformation that will happen to the rod. This deformation is a kind of strain. So we define what is called thermal strain. Thermal strain is deformation happening to the rod not due to mechanical force but due to increase in temperature or change in temperature. When we assume that we have this rod with initial length x naught and its temperature is increased by delta theta, we examine the increase in the length. We will note it by delta x thermal. We found that delta x thermal is proportional to x naught, the initial length of the rod. Also proportional to delta theta. For sure, if you increase more, you will have delta x thermal increased more and more. So we can write delta x thermal equals constant x naught delta theta. This constant, we noted it with alpha, the symbol alpha, which is called thermal expansion coefficient of the material. It depends on the kind of the material. After discussing what will happen with the increase of temperature, delta x thermal equals alpha x naught delta theta. This increase in the length of the rod is a kind of strain. Again, we can define the thermal strain as delta x thermal, the increase that happened, relative to the initial length of the rod. Delta x thermal equals alpha thermal expansion coefficient x naught delta theta. So I will divide alpha x naught delta theta by x naught. So the thermal strain will be alpha delta theta and no units. Why no units? Because it's a relative change. Length divided by length will give no units. Okay, this is a thermal strain that happens due to increase of temperature and is not because of mechanical force. This can happen and will not affect anything about the rod. But this thermal strain will make mechanical force if I put this rod between two rigid walls. I will study the case when I put this rod between two rigid walls. Thermal expansion happens between two rigid walls. You put the rod between two rigid walls and you increase its temperature delta theta. You increase the temperature you heated it. What will happen? It will try to increase in length delta x thermal, but the rod is stopped by the walls. So the walls prevent this increase, as if compressing it back, as if making mechanical force back on the rod. To study this, we put the rod between two rigid walls and we say that the delta x total is zero, which means that the total change in the length of the rod is zero and preventing it from any change. No change in the length of the rod. This change comes from two factors. The first one, due to increase in temperature, we have delta x thermal. And the other one, because of the pressing back of the walls. The walls are compressing the rod again. Delta x thermal plus delta x mechanical equals 0. Divide both sides of the equation by x naught, the original length. Strain thermal plus strain mechanical equals 0. But we know from the other slide that the thermal strain is alpha delta theta, depends on alpha and delta theta. And the thermal strain and the mechanical strain is stress over Young's modulus. Add two terms and the result is 0. I want to get force alone, so I will have this term the other side, negative alpha delta theta. I will put instead of the stress force over area, and I will get force in the left hand side alone. The force equals negative alpha EA delta theta. We have a negative sign for the force, which means that it is a compressive force acting on the rod from the two rigid walls. As we explained, preventing the rod from increasing in length is a compressive force exerted by the walls on the rod. This is very important in designing any rods between two rigid walls. You have to take care how it will react after increasing the temperature. Now we will discuss the other topic of elasticity, which is volume elasticity. We want to discuss what will happen in the volume or the bulk elasticity. This is a special case of multi-axial loading in 3D. The conditions that we have equal stresses in all directions. Now we have stress in the 3D. So the volume stress is proportional to the volume strain. The constant of proportionality in this case is called the bulk elasticity modulus. Its symbol is K, and in some references they use B capital. To use this law, we must have equal stresses in all directions. So the volume stress equals bulk's elasticity modulus multiplied by the volume strain. The volume strain, as all other strains, is relative change in dimensions. Now it's delta V over V naught for the bulk elasticity. This case happens a lot when we discuss the pressure. The atmospheric pressure is compressive stress from all the three directions, as if I am applying stress in the 3D, applying it to the object. And we are subjected to atmospheric pressure all the time. So we have the stress is negative delta P because change in pressure is a compressive stress. We will discuss this in the example later and how to deal with change in pressure. The third topic that we want to study in elasticity is the shear elasticity. What is the difference between shear elasticity and longitudinal elasticity? Assume we have this parallelopipe which is fixed from the bottom and we apply this force on the upper area, but this force now is tangential to the area. This is the area and I'm applying this force tangential to the area, but the lower base is fixed. When I examine this case, what will happen that the plane, upper plane or the upper base will be shifted, but the lower base will be fixed. Imagine that this upper area is shifted. Concentrate on this point A. It will be shifted to another point A dash. And this corner will be shifted to another point. Similarly for this corner and this corner. And we redraw the red parallelopipe as shown in figure. So what will happen if we apply tangential force? There will be shift to the layers of the material. In this case, we define the shear stress as the force per unit tangential area. In this situation, we use tangential area, not the perpendicular. So the definition of shear stress is force per unit tangential area. We can write the shear stress T capital and subscript SH, or we can write it the symbol tau. If we have a stress, we have strain. Strain is defined as deformation of the material. So scientists said that the deformations that happened is the distance traveled by A to A dash. This distance is called delta X. Now, delta X is not an elongation. It's a distance traveled by the layer, the upper layer. So the shear stress is defined as delta X divided by the height of the parallelopipe. H is the height of the parallelopipe or the cube used. From trigonometry, if you concentrate on this triangle, this side is delta X and this side is H. I will name this angle gamma. I will name this angle gamma. Tan gamma from this triangle is delta X over H. So delta x over h is tan gamma, another form of the shear strain. But for small angles, tan gamma approximately equals gamma, which is in radians. Don't forget that delta x is the distance traveled by point A to go to A dash. So, discussing the shear elasticity, we defined the shear stress as force divided by tangential area, and we defined the shear strain as delta x over h or tan gamma. What is the relation between the shear stress and the shear strain? Again, for small stresses, they are proportional. And the constant of proportionality is called the rigidity modulus. Its symbol is G capital, and in some references, it's called S capital shear model. The same as the discussion we discussed in the longitudinal elasticity. And also don't forget that we still have the elasticity energy distance, energy density, which is joule per meter cube, energy stored per unit volume. In this case, it's half shear stress multiplied by shear strain, or we can use this other form. Thank you for your listening.